Let's look at one idea to deal with problem 1 in our typical finite section method setting. And this is X is a sequence space over the natural numbers, and we take L2 because we want adjoint operators, so we need a Hilbert space. And for Pn you take the typical truncation operator that just stays with the first n entries and deletes the rest, are replaced by zeros. Then our expensive to compute expression, if you express it via matrices, looks like this. So let's compute this factor here and that factor here. And if you left multiply your matrix A star with this Pn truncation operator or matrix, this means that the first n rows of A star survive and the rest is deleted, put to 0. And similarly, if you right multiply your matrix A by the truncation Pn, then the same happens with columns. So the first n columns survive and the other columns are all deleted, replaced by zeros. Okay, now it's about computing this product here. And that looks indeed expensive because you still have infinitely long rows here that you have to multiply with these infinitely long columns here, and that just gives you one single entry of your product. So indeed that is costly. And then you get the following idea. In many applications, your matrix A is what is called a band matrix. So it only lives on finitely many diagonals, typically the main diagonal and some neighbors. So A is only supported on this light blue band, and everything outside is 0. In many other applications, it's not like that, but you typically have a decay. So entries are going to 0 as you go away from the main diagonal. But let's, for simplicity, start with this band matrix case where only finitely many diagonals are non-zero and all the rest is 0. Then your A star has, of course, the same band here, only transposed and complex conjugated. And then you would see the similar band down here, and of course also here. And then you could say, well, actually, the rows of this infinite matrix here are infinitely long, but after finitely many entries, there's only zeros. And the same is true here. So only the first n plus something entries of these columns are non-zero. And then after a certain cut, you get zeros only. And this is where you could do this cut here and here. And let's try to find out where that is. Okay, so this is your main diagonal, so that about here and here there is position n. Well, because you know that from your main diagonal down here the distance is n, so the same distance over here must also be n. And similarly here, right, you're saying that this is n, so also that must be n. And then onto that position n, you have to add this little bit, which you typically call the bandwidth of your band operator or band matrix. And because of the little w in width, you typically call it w, so that your cutoff position, which is at this length, can be computed as n plus w. And let's abbreviate that by m for simplicity. And then what I'm saying here is that we could simply squeeze another cutoff Pm in here, which would be in here, without changing anything, because all you cut off is zeros behind this or below that line. So this Pm here can be squeezed in without changing the result. if A is a band operator with bandwidth little w. And the m that we're writing here is actually a function of n. It is n plus w. If you're not a big friend of matrices, then you can see the same effect also in operator perspective. So let me start with a vector x from L2, which could be non-zero everywhere, infinitely long, and then apply Pn to x, which gives you the same vector but only supported on the first n entries, the rest is deleted. And then apply your operator A. And because by our assumption A is a band operator with bandwidth little w, it can transport data or information, if you like, only over distances less than or equal to w. And because the data only used to sit in positions 1 up to n here, it's going to sit in positions 1 up to n plus w here. So the rest down here is zeros. And that's why you can apply another truncation now at point M without changing the vector. And that's exactly what I was saying above here, only in terms of matrices. Now you will say that in many applications your operator or matrix A is not of this type, at least not with a sufficiently small bandwidth, because it has entries, non-zero entries everywhere. But very often these entries go to 0 as their distance to the main diagonal grows. And then you can approximate your matrix A by a band matrix of that style. And the bigger you take the bandwidth, the smaller your error is going to be. So you can at least approximate this expression by expressions where the PM is squeezed in. And we will argue that such a small error will not affect what we're going to say next. Okay, so let's study this new system with this squeezed in PM. And now let me make one more comment. Above here and again here, we argued that this operator here, PMAPN, is the same as the operator APN without the red PM, if A is a band operator of the corresponding bandwidth, or in other words, if A can transport information only over distances less than or equal to W. But then you could repeat the same argument for A star in the other direction, or you could simply take the adjoint of this equation. Let's do that. And of course we know what the adjoint of a product is. It's the product of the adjoints, but only in reversed order. And then of course our PNs here, which just perform this truncation after the nth entry, are self-adjoint, so we can remove the little green stars at Pn and Pm. And we are left with this already announced equation for A star here. And what this is saying is that we could also have argued via these three operators here, and could have argued that also from that perspective you can neglect the red operator. But exactly by that same argument we can also squeeze in PM here without changing the vector on the right hand side. And now that's our new equation. We should give it a label, and we should probably start labeling our equations a lot earlier. Let me start up here. So this one is number 1, This here is 2, that is 3, and now we have squeezed in PM on the left and right, giving us number 4 here. Now, because PM is a projection, we can pretend we have a square here, and then you can put brackets here, and then for this left factor you follow this computation in the opposite direction, and then we have rewritten pretty much everything in terms of PMAPN. We can even do that here. Okay, and I think now that's good enough to rewrite equation 4 again, which is still the same equation 4, only looking a bit nicer. And maybe let's label this bracket here with, should we call it BN? So that here and here we get BN star. But now if you look at this pattern long enough, you see that this is just the normal equation for the least squares problem, or Ausgleichsproblem as you say in German. Bn xn is approximately equal in the sense of least squares to our right hand side b. I think that is worth another label, which must be 5. And now that new equation, well, it's not an equation, it's a least squares problem, number 5, looks a bit like the finite section method again. In fact, we would like to see Pn or Pm in front here, but we can get that done as follows. Just like here, where we replaced Pm by Pm squared, we could replace this Pm here by Pm squared, hence getting another Pm in here, and then here, and finally here. Okay, so let's try to see that in matrix perspective again, so we can all agree it's essentially the finite section method. So your infinite matrix A is truncated from the right by Pn, which affects the columns of A, and then from the left by Pm, which affects the rows. And now recall that M is a bit more than N. So this Bn here can be identified with that finite matrix here. And then you're looking for solutions xn only supported in the first n component. But then, however, your right hand side is just your original infinite right hand side truncated down to the first m components. And that's why we refer to 5 as the rectangular finite section method. And because now your finite systems are higher than they are wide, so you have more equations than you have unknowns, or you could say they are overdetermined, it's clear that you cannot expect equality here, so you would have to work with least squares. So let me sum up here. The least square solution xn of 5 is the solution of the normal equation 4, but 4 is, at least if A has bandwidth W, the same as, where are we? 3, just with these PMs squeezed in here and here. And 3 is the finite section method for the equation 2. And 2 is equivalent to 1 by this little trick. Let's write all that down. Okay, what a story. So to summarize the summary, if usual finite sections give you trouble, then try rectangular finite sections where you make your submatrices a bit higher than they are wide and use least squares instead of equalities, and you will always be fine. When we proved and published that stuff in 2007, I think, one of the referees told us that numerical analysts, people working in numerics, have been working like this since the 1960s, but they never had a proof. So it was good to finally have a proof for this procedure that apparently was common knowledge already in a certain community. And to celebrate the achievement even more, let's look back to the problems that numerical analysts had with our original approach. So the first point of criticism was that this is expensive to compute because you multiply infinite rows by infinite columns, and of course that is extremely costly. Okay, this cutoff idea of course removes that problem. So introducing this additional PM, which doesn't even make a difference if you're a band operator. And then issue number 2 was squaring your condition number, because you work with A star A instead of just A. By the way, we even solved that problem because in the end, when we said 4 is just 5 in disguise, we again went away from A star A down to just A. So also that problem was solved, because in the end, when you're a person working in numerics and you want to solve a least squares problem like this or that, then numerical analysts will tell you to not use the normal equation as a means of solution. That's what you do in linear algebra 2 when your matrices are just 3 by 2 or something. But when m equals 1,000 or 1,000,000 or something, then you shouldn't do that for exactly this reason, because you're squaring the condition number. So instead they say you should use QR decomposition and use that for solutions. So depending on who your linear algebra professor was, you might even have seen that one, otherwise you will see it in a numerics course. Okay, I guess that's what you call a happy ending.